So guys, we'll start. Just wait for 2 seconds. Yeah. So write the heading transient. Write your heading transient. Okay. Transient. So basically, what in a DC network, suppose we have a particular DC network, and if there is a element like R, L, okay, this kind of a network. I'm just assuming this kind of a network is there. Okay, so there will be, due to this inductor, now this due to this inductor there will be a some transient for a few seconds. Okay. Suppose actually you think like this, you have a switch like this, you have a supply like this. Okay, now the switch was open, the switch was open for a long time. At some particular instant of time this switch get closed. So due to this effect, na transient is occurring. Due to this effect the transient is occurring. So particularly, actually at the infinite time, what will be the value of a inductor? XL is what? XL is j omega L, right? The value of XL is j omega L. So this is our DC supply. If we are putting the value of a frequency, what the frequency we are getting? 0. Okay, frequency will be 0. This is j omega L, and we know this is the DC supply. So frequency will be 0. So it will behave like a short circuit only. Okay, but due to this switching effect for a certain times, a certain nanosecond or a microsecond, there will be the effect of inductor. It can be the effect of inductor, it can be the effect of capacitor. What the elements we are actually connecting, it's depend upon that. Okay, so write basically means write the actual meaning of a transient. Just write the definition of the transient. So write it down. Transient, present in a circuit, transient present in a circuit when circuit is subjected to, when circuit is subjected to any change, either by any change either by changing the source magnitude, either by changing, so source magnitude. So first the source magnitude was 0. When we connected, the source magnitude came some voltage. So that's why we are writing any change either by changing the source magnitude. Okay, or any circuit elements. So, or any circuit elements, provided the circuit consists of energy storage. This point is very much important. Provided that the circuit consists of energy storage element. And what is the energy storage element? Inductor and capacitor. So you will understand in a better way, don't worry. Like inductor and capacitor. Okay, because inductor does not. So this is a very important point, because inductor does not allow sudden change of current. Sudden change of current. Okay, and same for capacitor. Capacitor will not allow sudden change in voltage. Sudden change in voltage. So guys, what I wants to say you, suppose you have a circuit like this particular inductor, and here I having some particular V value. Okay, let me make it like this. Yeah. So if I have a inductor like this, so first the connection was like this, and then I have a resistor. Let me draw in a better way. So I have a R. So guys, what will happen if suppose this inductor was charging from 0 to some t second. So 0 to t second, the connection was like this. So what will happen? The inductor will store some energy. Okay, and the storage of energy we already derived in the first class, half Li square. I hope you remember, half Li square. Energy in inductor is how much? Half Li square. So what will happen if we at t second, at some point t, if the value of, if you will see like this, from 0 it was 0 from 0 to, just wait, yeah, so from 0 to t, the connection was like this. At t second, the connection move from this point. So see, our circuit will become like this, and whatever the energy was stored in this, the energy will get dissipated in this resistor. Okay, so let's suppose if I am taking this as a place of resistor, if I am taking it as a bulb. Okay, if this as a bulb I am taking, so initially my bulb was what? Off up to 0 to t second. When the switch at t second, when the switch moved from this point to this point, what happened? The whatever the energy stored in this, it will flow in this circuit, and this bulb will get glow for certain time, not for an infinite time, up to t to t1 second. This bulb will glow. So that's why we are seeing the bulb is glowing whenever means in that kind of a circuit. Okay guys, is this clear? As this part is clear, what's happening means energy is storing in inductor. Okay, and what you know what is happening, suppose first in current was coming like this, my I current was coming like this. Okay, my I current was coming like this, positive to negative. When I will move this switch from this point to this point, the current was coming like this. Now the current will move from this point. So this the sign of the current will get changed. Okay. Now
charging and discharging, right?
Yeah, it's charging and discharging. Exactly. Okay. So these things are happening. Okay. So I just give you a brief idea. We'll discuss in a very good way. In a good way. So okay. So this is the definitions I had given. Okay. So what is actually transient? Just make a graph. Okay. Make a graph like this. So if the current is moving like this, so basically this movement is known as a transient actually. This particular movement, suppose this is my t, this is my I of t, this is 0 and this is 2 second. So 0 to 2 second inductor developed some energy. When I move the switch from one position to another position, it will be in the steady state. So this is my transient part. Okay, so we'll see everything very in a very deep. So okay guys, write it down. Means there is a one assumption. Means we already discussed in the first class. IL of 0 minus inductor current will not allow the sudden change of current. So IL of 0 minus will be equal to IL of 0 plus, will be equal to IL of 0. What is 0 minus, what is 0 plus, I will tell you. And VC of, for capacitor, VC of 0 minus will be equal to VC of 0 plus, will be equal to VC of 0. Okay, this 0 minus and 0 plus means, suppose, yeah, it is connected like this. Okay, first, so you are changing the supply. Means suppose you are changing the supply at 2 second. At 2 second you are moving from this point to this point. Okay, so what I am telling, suppose you are having some IL current in this inductor. At before means it is my time. Okay, this is my time, 0 to at 2 second. So the initial phase means just before the 2 second, this is known as a 2 minus, means 0 minus we can say. And after the 2 second, just after that 2 second, it's known as 2 plus, and at 2 second it's known as 2. So same, at 0 second we are considering like this, IL 0 minus, IL 0 plus. So inductor current, when you will move the switch from the at 2 second na, at 2 seconds, so the current will remain the same. Suppose the 5 ampere current was flowing, if you will change the supply like this at 2 second, means at 2 point, some assume 2.00000 some value, at that second the current will remain the same. And before also at 1.999999 some value, that is you are considering as a 2 minus, so the current will remain the same. So that is the actual meaning of a 0 minus 0 plus. Okay, so write it down. At t is equals to 0 minus, what is the meaning of t is equals to 0 minus? Time instant just before the switching operation. Time instant just before the switching operation. And what is t is equals to 0 plus? Time instant just after the switching activity. Time instant just after the switching operation. Okay, and what is t is equals to 0? This is exact time instead of switching operation. Exact time instant of switching operation. What about t is equals to infinity? Steady state time. Okay, steady state after the switching operation means infinite long time when you done the switching activity. Steady state after the switching operation. Switching operation. Okay, guys. So note one point. We also consider, this is the important point. We consider steady state before the switching operation. Before the switching operation. You will understand this. Don't worry. Switching operation. Okay. And make one box. And this is a very important part of this chapter. Write it down in this box. Your IL0 plus will be equal to IL0 minus will be equal to IL of 0. And what about VC? VC0 plus will be equal to VC0 minus will be equal to VC of 0. Okay. So this is the basic part of the transient. This what I had given you a crux. It's a very basic parts of the transient. Now you will understand from the circuit analysis, what is the actual meaning of the transient. Okay, so what is the actual meaning of the transient? So suppose you have a RL network. Okay, RL network, source free RL network. Suppose you have a source free RL network. So source free RL network, we can take it like this. This is my write the heading source free RL circuit. Source free RL circuit. Okay. So suppose you have something, some network like this. Earlier it was having actually some source, positive, negative V of S, and the source was connected like this, the inductor. This inductor was connected like this, and this is my RL network. RL network. This was the position 1 and this is the position 2. Okay, now what I am telling, the switch is moving at t is equals to 0. Okay, so what is the meaning of this? At t is equals to 0 minus, if anyone asks you to draw the circuit, assume this is as a RS. If anyone will ask you what was the circuit at t is equals to 0 minus, so what will be the circuit at t is equals to 0 minus? V of S at t is equals to 0 minus. Before coming to position 2, the circuit was like this only, right? RS, and this was my inductor L. So we are assuming, means before this circuit, before we are bringing this position from this point to this point, my circuit was like this. Okay, So if I am assuming the time boundations from minus infinite to 0, 0 minus, that is my 0 minus. So it was at the steady state. My circuit was at the steady state. So in steady state condition, what I have to put, j omega l, my frequency was 0. So I am getting the XL value is how much? 0. The circuit is like this, positive negative V of S into R of S. What is the current? What kind of a current we'll get? I of 0 minus, I am assuming. So what will the value of I of 0 minus? Vs by Rs. Correct? Vs by Rs. And I am assuming this Vs by Rs as I naught, I initial value. Okay guys. And what is the property of an inductor? I of 0 minus will be equal to I of 0 plus, okay, is equals to I of 0, and we are getting that value as a I naught. So when at this point, when we will shift the position from 1 to second, what will happen? The circuit will become like this. Circuit will come like this, or this. Okay. So for t is greater than 0, our circuit will become like this. This is my RL network, and this was my positive negative V of L, and I am getting the current I. This is my L. Okay. Now if you will assume this is your positive negative V of R, so what the KVL equation you are getting, guys? What the KVL equation you will get? What the KVL equation you will get? V of L is equals to, or let assume V of R in this way. Okay, in this way, negative positive, because this current now, this the direction of, in this if the supply will be like this, the direction of the current will get changed. So current will start flowing like this. So that's why I am considering this as a positive negative V of R. Okay, wait, just wait. This, because the current is going like this. Okay, so that's why I am considering this as a positive negative. So what will be the equation? V of L is equals to V of R. Positive V of L plus positive V of R, you will get as a 0. Just I had applied the KVL. You will understood each and everything. Just have patience. V of L plus V of R is equals to 0. And what is the equations of a V of L? In our earlier classes, we know that V of L is nothing but L di by dt. L di by dt. And V of R means I into R. I current is going. It is equals to 0. If we'll derive this L di by dt, and it is minus I of R. Okay guys. And I am considering my current from at t is equals to, at we are taking at t is greater than 0. Okay, so at greater than 0 I having if you'll bring this side I, it will become 1 by I into di, and this will go dt into R by L minus R by L. Integrate both side. Okay, so current, initial current I am getting as a I naught at t is greater than 0, and it is going up to how much? I of t, infinite distance. So that's why I am considering I of t. and this is minus R by L, and I am taking the time 0 to t. So if you solve this, what you will get? Ln 1 by I as a ln of I naught into I of t minus R by L into t. Okay guys, if you put it, what you will get? I naught of t divided by I naught. Actually you will get ln I of t minus ln I naught. So ln log a minus log b is ln a by b minus R by L into t. If you solve this, what the equation you are getting? I of t you are getting as e power minus RT by L into I naught. Because if you will shift this log function this side, this is the formula. Ln a is, if ln a is equals to b, then what is a? A is equals to e to the power b. The base function is e, that's why. So I'd use this principle only, and I got the value of I of t is equals to I naught. Means you will get I naught of t divided by I naught is equals to e power minus R by Lt, and this I naught will get multiplied. So I naught into e power minus RT by L. So for a source free network, what is the current you are getting? I of t I naught e power minus RT by L. Now we got the equation for this particular network. Guys, we got the equation for this particular network. Okay, at t is equals to 0 plus, I'm considering at t is equals to 0 plus, my I of t value should become I naught. Put the value t is equals to 0 plus, you will get I of t is equals to I naught only. At t is equals to 0, put the value of t is equals to 0, you will get I of t is equals to I naught only. And what I am telling, if you will, this is what? This is one inductor, one resistor. So this inductor having some energy, it will deliver some energy, but it is not an infinite source of energy. So at an infinite time, this current will become 0. This current will become 0. Put the value of infinite. What you are getting? I naught of t is equals to 0. Right? So what I did it, we took one voltage source free RL circuit. We are discussing about the source free RL circuit. So my source was V of S, one resistor was connected. So what I am telling, from suppose from minus infinite to 0 time, the network was like this. The network was like this. So this inductor was storing some energy, half Li square. This inductor was storing some energy, that is half Li square. And if you will solve up to 0 minus infinity to 0 minus, so the circuit will be simple because it is disconnected from the switch too. So the circuit will be simple like this. And we know this is a DC current, this DC voltage, the inductor value will always be 0, short circuit. Why so? Because the frequency is 0. And it is operating at an infinite time, steady state amount of time, because we are assuming that it's operating from minus infinity to 0 minus. Okay, so my simple circuit will got Vs Rs. So what is the value of I you will get? Vs by Rs only. Apply the KVL. If you will short circuit this inductor, you will get Vs by Rs, and we are assuming this Vs by Rs is equals to I naught. So before closing the switch, before the switch was at one position that we are calling at 0 minus, I of 0 minus, I was having a current I naught, that value was Vs by Rs. Now I want a current, now I want the value of a current from 0 plus to t second. So we know that at 0 minus and 0 plus and 0, the inductor current will remain same. I of 0 minus is equals to I of 0 plus is equals to I of 0. Okay. And what is the inductor current? Always take like this. I of t. This is positive, this is negative. This is your inductor current and this is your VL of t. Don't change the sign and all, although the sign will be changed. Okay. So now what is happening, guys, now when the circuit is connected to this particular resistance, what is happening? My I of t is flowing like this. It's delivering the energy from this side to the resistor, and we are getting the VR value, and this is my VL value. So we are getting a one equation, VL plus VR is equals to 0. Now what I did, we know the VL value, VL of inductor is L di by dt, and V of R I just assume like this. Okay, V of R is I into R. I assume I into R. Okay, so if you will assume that L di by dt plus I of R is equals to 0, if you will solve this particular thing, L di by dt, it will go into minus I. I am considering this I as a function of time. Okay, I am considering this I as a function of time. And when I bring this particular I this side, and what is the integrations of 1 upon x into dx? It is log x. But I am considering this in the function of exponential, so that's why I am taking ln x. It's up to you. You can take anyone. So I am taking that the function of exponential function. So that's why I have considered that ln I function. And my initial current, the integration function is working from my initial current. We know at t is equals to 0 minus, we know that the value we got the value that is I naught, and it's going up to infinity, but we don't know the value at infinity, what will be the current. So I am considering I of t. So from I naught to I of t I am deriving these equations. That's why I have taken I naught of t and I of t. After putting the value ln I of t, this will be in this function ln I of t minus ln I naught of t, and the minus, we know that ln a minus ln b is nothing but ln a by b. So these things in a mathematics we will study, and so from this we got the value ln I of t divided by I naught of t and minus RT by L. Okay, after solving this I of t, we will get I naught of t e power minus RT by L. And we know that this inductor, it's like means if you have some energy in this inductor. Okay, suppose this is having some energy in this, and all of you know that energy can neither be created nor be destroyed. It can be transformed from one form to another form, right? So suppose this inductor was having a 5 joule energy. Okay, and if I am connecting this inductor with a resistor, this is my resistor, so 5 joule energy will get transformed in this resistor. Okay, it will get transformed in this resistor, and this resistor will dissipate this energy in the form of heat. So energy transformed in the atmosphere in the form of heat. Okay, if the energy will transform, if the all energy transformed in the heat, that means at infinite time my current will be here the current. If all the energy get transformed in this, so inductor value is becoming 0. So that means half Li square, half Li, L will always have some value. That means my I is becoming 0.
So why it is necessary to discharge the inductor value in resistors? What is the necessity?
What is the necessity of what?
Transforming the inductor energy and
actually see actually the thing is that now why we are storing this kind of a things now, what is the need of a capacitor?
for
Storage, right? For storage. So for making if you will go for a power electronic circuit, there we are using a filters and all. Okay, filtering circuit means our waveform. See, in a power electronics we have a rectifier, right? So rectifier, what rectifier do? It form, if you are using a full wave rectifier, so it's making a circuit like this, but it is not complete DC, right? My DC will be like this, na? So that's why that's why this energy kind of this kind of a inductor and capacitor will use the same concept, and the circuit will become like this, like this, like this. Means some word oscillation will get. The more filter we'll use, the more straight line we'll get. Okay, so we will see these things in power electronics. Okay, for
Yeah.
okay, so this is the thing of the inductor. So I hope you guys got this equations. I of t is equals to I naught e power minus RT by L. Up to here it's clear for everyone, or anyone is having any doubt? Priyanka, it's clear for you? Prasanna?
Yeah.
Okay. Raj, for you? Corridor for you? Okay. So guys, okay, we got the result. Okay, now tell me one thing. What the value of an inductor we get? We get the value of a I. I of t is equals to I naught e power minus RT by L. And what is the inductor value? V is equals to L di by dt. So what will the value of an inductor? L into differentiate this. I naught e power minus RT by L into d by dt. So if you will differentiate this function, this is your function. This particular, this is your function. If you will differentiate this, what you will get? L into I naught e power minus RT by L minus R by L. So it will get cancelled out. So what you will get? Minus I naught into R e power minus RT by L, VL of t. Okay, we just did the differentiation. This is my constant part. So integrations of e power minus differentiation of e power minus x is e power minus x only, and differentiation of e power minus ax is a e power minus x. Okay, minus a e power minus x. Sorry, minus a will come. So here, what is the terms? Are constant terms. So minus r by l. So that's why minus r by l is coming outside. Okay. Okay, guys. So we just put v is equals to L d by dt. This is my I current, I naught e power minus RT by L. If I'll differentiate it, I will get minus I naught into R e power minus RT by L. So this is my V of L value. So we know the equation of a V of L plus V of R is equals to 0. Then what will the V of R value? Minus V of L. So V of R is I naught R e power minus RT by L. Is this clear, guys? Okay, guys, if this part is clear, you have to tell me the graph of this. So suppose we have this is t function, this is my I of t function. If I want to draw the graph, so what was the I of t? I of t, this is my 0 at 0 position. Before that it was at a steady state condition. So I of t was how much we got the value of I of t? I of t I naught e power minus RT by L. I naught e power minus RT by L. So at t is equals to 0, what is the value of I of t? At t is equals to 0, I have I naught value. Okay, and at t is equals to infinite, I have 0 value. If you will put the infinite value, you will get 0. So my figure, this figure will exponentially decrease. This is I naught e power minus RT by L. So this was the figure for I of t. What about VL of t? So VL of t, what you are getting? VL of t is equals to I naught into r e power minus RT by L minus. So if you are forming a graph, this is your t function and this particular is your v of L function. So at t is equals to 0, what is the value of a v of L? Guys, at t is equals to 0, what will the value of a v of L? If this you will put 0, so this will become 1. E of 0 is 1 only. So you are getting minus I naught into R.
Minus I naught into
R, yes. You will get minus I naught into R. And at t is equals to infinity, what you will get? E power minus infinity? 0.
0.
So the graph will be like this. Okay. So this is the v of L minus I naught into R e power minus RT by L. So this was the concept for v of L. What about v of R? V of R we got I naught into R e power minus RT by L. Okay. So this is my t, this is my v of L, v of R. So what is the value of at t is equals to 0? T is equals to 0. What is the value? I naught into R. I naught into R. And at t is equals to infinity, the value will be 0. The graph will declining like this. So I naught into R e power minus RT by L. I hope you got these things. So write it down. One important things in discharging inductor, the current direction remains same. The current direction remain same, but the voltage polarity reversed. So see, this is my voltage, it's getting reversed, it is discharging. Okay, but if you'll see for an inductor, in the case of inductor, the current is discharging only, this part is discharging only. So positive, this the direction is positive, this not cross the 0 point, but your v of L, it is in the negative axis. So that's why in discharging inductor, the current direction does not change, but the polarity of the voltage get reversed. In discharging inductor, the current direction remains same, but the voltage polarity reversed. Okay guys, how so? Means suppose I am giving you in a brief idea. See, this is my v of S, and first it was charging. Okay, so current was coming like this only. So this was my positive, this was my negative. Okay, now what is happening when I am connecting this inductor with some load? Here also some resistance I am considering, and here I am. So the current is flowing in this direction only. Okay, so that's why it's positive, negative, it's coming. But you know, if the current is flowing in this particular direction, this current is starting from this particular direction. So this inductor is what? It's a current source. It's behaving like a current source and is delivering some current in this. That's why I'm taking this as a positive, negative. So earlier the polarity was positive here, negative here. Now the polarity is positive, negative. So you don't confuse, you just do with that numerical like this. You don't have to confuse, means you don't need to change this polarity, just do like this only, you will get the answer in a correct way only. I will show you while we'll do the numerical. Okay, but remember, this point is very much important. For inductor, the current directions will remain same, but the voltage polarity will get reverse, because we are getting the negative voltage minus I naught into R e power minus RT by L. Okay, so write the next topic, that is energy concentration. Energy concentration. So we all know, because we already discussed in the first class itself, energy stored in the inductor is half L I of t square. Okay guys, so half L, and what is the value of RL, source free RL circuit? We got I naught e power minus RT by L the whole square. So what you will get, half L I naught square e power minus 2 RT by L. Okay, and yeah, this time constant for this source free RL network, na, what is the time constant? Write it down, the time constant. See this e power minus t upon, we can write R by L as a L by R. So this L by R is your time constant. So tau is equals to L by R. The value of a L by R will give you in a second. So second will get cancel out, and you will get one constant value. Okay, so we can write this equation as a half L I naught square e power minus 2t by tau. Okay, so this is your WL of t. WL of t. So guys, if you will put the value of t is equals to 0, what you will get? WL of 0 half L I naught square. Okay, right, you will get this. So we can write the equation WL of t as WL of 0 into e power minus 2 t by tau. This part. Clear? And if you'll go for the energy in resistor, WR of t, so what is the formula for finding the energy in a resistor? 0 to t P of t into dt, power into time, integrations. Okay, from at what time it's happening. So you need to do what? Put the value of a power. Power will be V into I, V of t into I of t into dt. Okay, what was the VR of t you got? What was the VR of t you got? 0 to t, and VR of t, the value we got I naught into R e power minus RT by L. So I am writing minus t by tau. Here tau is L by R. Okay, and what about the current equation you got? I naught into e power minus t by tau, integration. Okay, so if you solve this particular equation, what you will get? I naught square R, this all are constant term, 0 to t, and this all get added, e power minus 2t by tau into dt. Okay, so if you will integrate this, I naught square into R, if you will integrate this, e power minus 2t by tau 0 to t into, in integrations what's happening? It will come 2 by tau by 2, constant is getting divided. So put the value put the value of everything and tell me the results. You are getting minus 1 by 2 I naught square r, and tau value is L by r. And this, if you are putting the value, you are getting e power minus 2 t by tau minus 1. Okay, so this part getting cancel out, and this is your L value. So you are getting, if you'll take the minus inside, half I naught square into L 1 minus e power minus 2 t r by L. I am putting the value of this. Okay, so guys, what you are getting, the energy of resistor is half L I naught square into 1 minus e power minus 2t by tau. Just consider like this, L by r as a tau. So this is my this particular is my formula for energy stored in resistor. See what I did. Energy for inductor, it's a half Li square, everyone know. I just put the value of I of t, what we derived, and I of t value is I naught e power minus RT by L, the whole square. After this calculation, I am getting half Li naught square e power minus, substituting the value of a square, will get this things. And if we'll put the value of a t is equals to 0, we'll get this e power minus 2 0 by, so it will become 1 only. So half Li naught square will get. So what I am doing, I am putting this equation WL of t, instead of half Li naught square, I am putting WL0. So we are getting like this. Okay, now what is the energy of resistor? If you have a resistor, okay, this resistor, so what will the energy formula for resistor? W is nothing but 0 to t P of t into dt. And what is P of t? P of t is the product of V of t into I of t. We are seeing for resistor, that's why I am writing VR of t, and I of t current will be the same only. So what is the value of a VR of t we got? I naught R of e power minus t by tau, and I naught e power minus t by tau. So this particular things are constant. So that's why I am taking outside I naught square into R, 0 to t, and this will get added, so it will become e power minus 2t by tau. Tau is L by R, initially I told you. Now if you will, integration of e power minus ax into dx will be e power minus ax by minus a. So this is the integration formula what I had used here. So after using this, I am getting the value like this, and this tau is what? This tau is L by R. After substituting this, I am getting minus half I naught square into R into L by R. So this RR will get cancelled out, and I am putting this all value, substituting this all t and 0 value, I am getting this, and when I am transferring this sign this side, I am getting 1 minus e power minus 2t into R by L, and after that I just converted in the function of a time constant. So I got the energy stored in resistor, this value, half L I naught square 1 minus e power minus 2t by 2. Is this part is clear for everyone? Is this part is clear for everyone? Prasanna, for you it's clear. Raj, for you it's clear. Priyanka, for it's. Prasanna, just tell. Is this clear?
Yes.
Priyanka, for you?
Not really.
Okay. So you understood these things. Okay. So guys, what I want to say you, see, so what is actually means, if you want to represent WR of t in terms of WL of t, half Li naught square was WL of 0 into 1 minus e power minus 2t by tau. Okay. And if you want to make the curve of inductor, energy stored in inductor, this is WL of t. The value we got WL0 e power minus 2t by tau. E power minus 2t by tau. So if you substitute the value with respect to time, so at t is equals to 0, we'll get WL of 0. And it will get decrease like this. At infinite, it will become 0. Okay. What about inductor is to energy stored, energy dissipated in resistor? It will not store, it will dissipate. So that's why I am telling dissipate. So earlier, if you'll put t is equals to 0, so if you'll put t is equals to 0, what you will get? 1 minus 1, 0 only. So initially the resistor was having how much energy? Zero energy. Then if you will put the value of a t is equals to infinite, so if you'll at infinite, this e power minus 2 infinite by t is it will become 0. So you will get WL of 0, right? If you will put t is equals to infinite, so e power minus infinite is 0. So you will get, and 1 minus 0 will be 1 only, so WL of 0. So at infinite time, what energy you are getting? WL of 0. So this is what this, it is exponentially increasing function. So this is the graph for resistor, and this is the graph for inductor. So inductor is discharging its energy, and resistor at beginning the resistor was having 0 energy, then it start getting the energy from inductor. So it gets some energy, until and unless it's reaching up to the saturation point, means overall energy condition. So this is the story of a RL network, source free RL network. If anyone is facing any doubt, they can ask, or otherwise I will go for the next topic, that is source free RC circuit. So the same concept will get repeat. So that's why I'm asking, if anyone is having any doubt, any small doubt is there, they can ask. Okay, fine. So the next topic is source free RC circuit. Okay, this is my source free RC circuit. So what will the diagram for the figure for this? This is my RS. This is at position 1. This is my capacitor. I'm assuming current IC is flowing in this. This is positive, negative, VC. Okay, and this is my positive negative V naught, and this particular is my register, R register, and this is my switching position 2. At t is equals to 0, the switch is moved. So guys, what will be the figure of this circuit at t is equals to 0 minus? At t is equals to 0 minus, before closing the circuit to the switch 2, what will the figure? The figure will be like this. Right? Before moving to position 2, the figure will be like this. And what is actually capacitor? Capacitor is minus j by omega c. So we have a DC value, that means the frequency is 0. If we'll put the frequency 0, what value you will get? Minus j divided by 0 is infinite is coming. That means what? That means at infinite amount of time, my circuit will become open circuit like this. Right? So if it is an open circuit, so what will the current will flow? Zero current, because it is open. So if the zero current will flow, so this I am assuming as a plus minus Vc. So if you apply the KVL, what value of a Vc you will get? V naught only. Minus Vc plus 0 into Rs plus Vc is equals to 0. So what? Minus V naught. So what value of a Vc you are getting? Vc is equals to V naught only. So this is 0 minus voltage. Vc 0 minus voltage, I am getting V naught. And we know in a capacitor, Vc 0 minus will be equal to Vc 0 plus will be equal to Vc of 0. So now at 0 time, when we move the at that time when we move the switch from this position to this position, my circuit will be how much? It will be look like so some resistor will come. Yeah, that resistor will come. So the circuit will look like this, na? And I had assumed current directions. Okay. In this way only, IC of t I am taking. And this is my C, and the capacitor value I am getting positive negative. That is my Vc only. Okay. So guys, this particular things I am getting. Okay, my circuit is becoming like this. Now what I am saying, because the voltage, see the polarity of the voltage, it's positive, it's negative, and it will behave as a battery. The current will start from flow from positive terminal to negative terminal. So that's why I have to consider my IR of t in these directions, because I am getting positive negative here, and it's becoming, that capacitor is becoming as a battery, a storage battery. So it will start delivering the energy from this point, this particular R. And what is the equation for okay, even yeah, that things we wrote. Okay, so guys, what is actually, if you'll apply the KCL, what is IC of t plus IR of t? It will be 0. if current is like this and if current is like this, so basically your IR of t is opposite to minus IC of t, right? We just took the reverse direction. Okay, and if you will see the capacitor current was, we have to assume like this only, IC of t, I have to assume like this. Capacitor current, what I had assumed, I will not interchange. Okay, so and now because of this polarity, I have to assume this is becoming as a battery source and it will start delivering a current from this position to this position. So that's why I'm taking IR of t. Okay, so what is and this is your VC voltage, so this will also my VC voltage. This is, if this is my VC voltage, so this is parallel to this, so this is also my VC voltage, right? So what will be the value of IR? IR will be VC by R. VC divided, this is R, so VC by R, IR will, we will get IR value is VC by R. And what is the equation for capacitor? IC of t is equals to C dVC by dt. This is the equation from the first class we know. So we will substitute the value C dVC by dt plus IR of t, we got VC by R is equals to 0. So if you solve this particular thing, C dVC by dt is equals to minus VC by R, right? So bring this part this side, dVC divided by VC, and take minus 1 by RC this side and bring this dt this side. Put the value. Now the condition is what? We are assuming at t, we are finding the value of a VC of t from 0 to t, from 0 to t, so 0 to t, and we know that at 0 time, at 0 time we have a VC of 0, that is equals to VC of 0 minus, and it will be also be equal to VC of 0 plus, this is minus. So and that value, what we got, VC 0 minus value, we got V naught. So this is my V naught, and at t we are considering VC of t, so that's why I am considering here VC of t. After solving this, I will get ln VC of t divided by V naught, and it will be minus 1 by RC into t. Taking log this side, I will get VC of t divided by V naught e power minus t by RC, and VC of t will be equal to V naught e power minus t by RC. So this is the equation for a voltage we are getting. VC of t is equals to V naught e power minus t by RC. And what is the time constant here in RC network? Tau is R into C only. So time constant will be R into C for RC network. Okay, now you got the value of a VC of t, V naught e power minus t by RC. So what will be the value of a IC of t? C dV by dt, dVC by dt. So C into d divided by dt, and what is the VC value? You got V naught e power minus t by RC. So you will see automatically your capacitor current directions will change from positive to negative after solving this. C V naught by RC minus e power minus t by RC you will get, and the value we are getting in a negative, minus V naught by R e power minus t by RC. This is your IC of t, and we know that IC of t is equals to minus IR of t. So IR of t, you will get V naught by R e power minus t by RC. So if anyone means, if you want to draw the curve, how you will draw? If I am considering this is my VC of t and this is my t, so VC of t value, what we got? VCT of value, we got V naught e power V naught e power minus t by RC. So at t is equals to 0, how much voltage we are getting? V naught value. And at t is equals to infinite, what value we will get? 0 value. So this is decreasing curve, exponentially decreasing. What about IR of t? The equation is, the IR of t equation is this. So this is, I'm considering my IR of t and this is my t position. So at t is equals to 0, what will the curve? V naught by R. And at t is equals to infinite, it will be 0. So what will be the curve? It is exponentially again decreasing. And if anyone will ask you, what about IC of t? So this is my IC of t. And the equation of IC of t is minus V naught by R e power minus t by RC. So at t is equals to 0, how much value we are getting? Minus V naught by R. And at t is equals to infinite, we are getting 0. So the case of discharging, we are drawing this curve in the second part, that means it's discharging. Okay, so write it down. In discharging capacitor, the polarity of the voltage, across the capacitor does not change, but the current direction will change. But the current direction are changing. So means what I want to say you guys, see, so earlier we are taking means the current, like IR is equals to this current I am assuming as a 0. So this is a 0, we are taking the current like this only. Okay, okay, this current is coming like this. So now what is happening now, when you are making the circuit like this, so earlier the current was coming like this, but this IC value now, while deriving, we are getting a negative. If it is coming in a negative, means what? The current get reverse. So that is the actual meaning. So that's what we had written. In a discharging a capacitor, the polarity of the voltage across the capacitor does not change, but the current directions are changing. And you can see in the figure itself, your current directions is coming in a negative. We had assumed in a positive way, but it's coming in a negative. So our direction is getting changed. So what directions is changing? It is negative. This part you can see it's negative. But voltage polarity, you see the voltage, it is in the first quadrant only. That's why we had said the polarity of the voltage will remain same. It's not crossing the 0 point, it's not coming downside. Okay, this is the story of RC network. So up to here, Prasanna, it's clear?
Yes, sir.
For you, Priyanka? Or any doubt? If you are facing any doubt, you can ask.
No.
Raj, for you, it's clear? This.
Yes, sir. Clear.
Okay. So, yeah. Now the same thing we'll do. We'll do the same thing. The energy concentration. Okay, guys. Energy concentration. So what is the energy for capacitor? Energy for capacitor was, we already discussed these things, half CV square. So I'm writing Vc of t square. So if you'll put the value of Vc of t, what value we got? V naught e power minus t by Rc the whole square. So Wc of t, what we are getting? Half C V naught square e power minus, I am writing Rc as a tau, it in 2. So Wc of t, what we are getting? Half C V naught square e power minus 2t by tau. And if you will put the value of a t as a 0, what you will get? Half C V naught square. So this can be written like Wc of 0 e power minus 2t by tau. And what about your energy that dissipated in resistor? I'm just telling the wrong word, store. So resistor will not store the energy, dissipated. So the formula for dissipated of the energy dissipated in the resistor is what? 0 to t p of t into dt. So Wr of t, put the value 0 to t. So voltage was Vc of t only, and current was IR of t dt. Okay. So put the value of a Vc of t. Vc of t value was V naught e power minus t by tau. Instead of Rc, I have written tau. What about IR of t? It was V naught by R e power minus t by tau into dt. So if you solve this, you will get V naught square by R e power minus 2t by tau, 0 to t into dt. Okay. And solve this equation. V naught square by R minus tau by 2 e power minus 2t by tau, 0 to t. So this, instead of tau, I am writing Rc. So if you put the value of Rc, let me write here Rc value only, R into C, so it's get cancel out. So you will get V naught square C, minus term is there, 2 is here, e power minus 2t by tau minus 1, and take this minus this side, you will get V naught square C by 2, 1 minus e power minus 2t by tau. So this is your energy in resistor, and this was the energy in capacitor. You can write it like this also. Instead of a half CV square, you can write WC0, right? WC0. So let me write like this only. Wr of t is WC0, 1 minus e power minus 2t by tau. So guys, if you will draw the curve This is your T, this particular is WC of T. If you'll draw the curve, what you will get? This at T is equals to 0, WC of 0, and at T is equals to infinite, this will decline like this. What about the WR of T? WR of T. So at T is equals to 0, if you put the value of a T is equals to 0, you will get 0. 0. And at T is equals to infinite, you will get, I am considering this as an infinite, you will get WC of 0. At T is equals to infinite, because it will become 0. So the curve will start increasing like this, increasing like this, increasing like this. So this was the story of a RC network. Okay guys, this was the story of the RC network, source free RC network. So from this, what we understood? From this we have a one important thing, that is a very much important thing. This is your R, this is your I of R. If you are considering your IC in this, so your IC will, polarity of the voltage will be that only, but the directions of IC is changing. Okay, the directions of IC is changing. And for inductor, what's happening? What was happening for inductor? Current direction was same. Current direction, you had assumed the current directions like this, and this was your positive negative V of L. This positive negative V of L. But what happening? While changing, your polarity is getting reversed. Voltage polarity is getting reversed. We are getting the negative voltage. This is V. Okay. So IC is C dVc by dt, and I is minus IC. And what about this? VL of T is L di by dt, and V is minus VL. So this is the important things. And write the definitions. One thing I just forget to tell you guys, what is the meaning of time constant? So can anyone tell me what is the actual meaning of a time constant? What is the definition of a time constant? It's a very important question in an examination, in an interview. They are asking what is time constant. So you will say what is time constant. So you cannot say L by R, the ratio of inductor by ratio. Yeah, it is true. The R into C, time constant is R into C. But what is the actual meaning of a time constant? Write the definition of a time constant. Okay, write the definition of the time constant. It is the time taken by response. It is the time taken by the response to reach 36.7% of its initial value. While discharging. or decaying, or it is the time taken by the response, or you can say, or it is the time taken by response, it is the time taken by response to reach 63.2% of its initial value while charging. Okay, so see, so charging, discharging, you guys know na, understood na? Charging, what is the charging and what is discharging? So this is my charging, and if I want to tell you about discharging, so it will discharge like this. Okay, so if you are telling in regarding with the charging, so what is time constant? Suppose this position, your final position is this is your final position. So the value of this will be 0.632. At what time you are getting the 63% of the overall value. Okay, so this is your time, and while discharging at the same time, the curve will be 0.367. okay, so suppose means what I want to say you, suppose we are talking about the inductor. Now you will understood in a very perfect way. So guys, what I want to tell you, the inductor, so circuit is like this. Suppose positive, negative, your R value is here, and you have a inductor value. Okay, so while charging the inductor, so the final value, suppose it's 5. Okay, so my inductor is reaching the final value 5. This is 5. What is the 63% of the 5? What is the 63% of the 5? 5 into 63.2% divided by 100. Tell me the value. Guys, use the calculator and tell me the value. 5 into 63.2. How much we will get?
3.16.
3.16. So suppose we are getting a 3.16 value at this time. Okay, this is my t. So this will be my this is my time constant. Okay, now if I'll talking about the discharging case, this is my charging case. If I'm talking about the discharging case, so the inductor will start discharging from the final value. This is my 5. Okay, so it will start discharge. What is the 36.7% of the 5? What is the 36.7% of the 5? 5 into 36.7 divided by 100. Tell me the value. This is your discharging case. What value we will get? 5 into
1.8.
1.8. So this 1.8, at what time the 1.8 is coming while discharging these things? Okay, so this is the meaning of the time constant. So I told you about the inductor. Okay, the same thing is happening with a capacitor. With capacitor we'll see voltage. Okay, because capacitor will store voltage. Some voltage will come, and at a point will come, it will store the maximum voltage. So that will become the maximum voltage. Okay, this is the current. So this is I and this is T. Okay guys, so write one thing, total response. What is the meaning of a total response? Total response. Total response is nothing but it's a natural response. Natural response plus forced response. Forced response. So natural response, the meaning of a natural response is transient, what we had discussed, and we can say in a transient we basically no source present, no source present, or we can say ZIR response. Okay, we will discuss ZIR, concept of ZIR in control system, and complementary function. We'll discuss these things in a maths, complementary function or particular integral. Okay, I will tell you right now also, but in a very short way. We'll discuss in a deep in a maths. Okay, and this is our steady state. Forced response is your steady state, and here ZSR is coming, and particular integral. Okay, so we'll discuss these things. For right now, you just write that total response is a natural response plus forced response. So for natural response, transient will, and for forced response, steady state will occur. Okay. For the happening of the natural response, we use the transient function, and for the happening of the forced response, we say it's because of the steady states. Okay, the same thing we can say transient as a ZIR response or a complementary functions, and for the steady state we can say ZSR response and your particular integral. Okay, so ZIR concept and ZSR concept will come in a control system. We'll discuss these things. Okay, so write it down. This is the theory part. Any electrical network consists of two type of response. Okay, one is force response, that is your force response. One is your force response and another is your natural response. So first write the things about the force response. The response of a network, the response of a network, the response of a network when source present in it, the response of a network when source present in it is called force response. Okay, the response of the network when any source present in it, when source present in it, it is called as force response, forced response, forced response. Okay, and it leads to a steady state response, and it leads to a steady state response. response. Okay, this response is independent of a this response this response is independent of the nature of a passive element. This response is independent of the nature of a passive elements. Okay, passive elements, and depends only on the type of the input, and depends only on the type of input, and this response can be obtained by solving the particular integral, and we'll see the numerical of this. And this response can be obtained by solving the particular integral pi. Okay, particular integral, part of the differential equation, differential equation. So what is the force response? The response of a network when source present in it. Either it will be a voltage source, current source. So source present in it. Okay, and it leads to a steady state response. Okay, this point is important. It's lead to the steady state response. This response is independent of the nature of passive element. So what is the meaning of a passive element, guys? I think you remember what is the passive element and active element. So what is the meaning of a passive element? And a passive element is an electrical component that does not generate power, okay, but instead dissipates or store or release it. So passive elements include resistance, capacitor, or a coil. So your all RLC networks are a passive elements. So, okay, so this response is independent of the nature of a passive element. So, and it will depends only on the type of the inputs, means what the things you are providing, voltage, current. Okay, and response can be obtained by solving the particular integral. So you will understand in a better way while deriving the equations. Okay, so this is about the force response. Write the next topic, that is natural response. Natural response. This is natural response. So the response of a network, the response of a network without the source present in it, is called as natural response. Okay, and it gives the transient response, and it gives the transient response. Okay, guys, this response depends on the nature of this response depends on the nature of passive elements, nature of the passive elements, RLC, that is passive elements. Okay, and it is independent of the type of input, and it is independent on the type of input. So this response, how we'll solve this response? So this response is governed by the characteristics equations. Characteristics equations. Equation of the circuit. Characteristic equation of the, what is the characteristic equation of the circuit of any RLC network? We'll see it, of the circuit, and it can be obtained by the solving, and it can be obtained by solving the complementary functions, okay, in differential equations. So this is complementary function in differential equations. Okay guys, now we'll discuss what is the how the things is coming. So natural response and forced response. So suppose you have a RL network. Okay, this is the things you have. Positive, negative, this is V of S, and the switch is getting closed at t is equals to 0. This is your network. Okay, and we know the conditions of because this is the series with R, so I of 0 plus will be equal to I of 0 minus will be equal to I of 0, and this is 0 because initially the current was, that switch was open, so no current was flowing, so that we took it as a 0. When we will connect this, we'll get the circuit like this, right? V of S, we'll get the circuit like this. What is the equation of a V of S? You will get V of S equation, what you will get? This is R, this is L. So V of S is equals to I into R plus the voltage across this inductor will be L di by dt. So divide means we need to solve the differential equation. So divide all the elements by L. So you will get Vs by L is equals to I R by L is equals to plus di by dt. This is your plus di by dt, right? We are taking L as a common. So if you take the L common, what you will get? Vs by L, I R by L plus di by dt. Okay. So guys, you have the differential equation di by dt is equals to Vs by L minus I into R by L, right? This is your differential equation. So I of t, you know, you need to calculate the value of I of t. So I of t is the function of two differential equation. One is the complementary functions and one is the particular integral. So for complementary functions we are getting a natural response, and for particular integral what we are getting? Force response. Okay, so I hope a little bit maths you guys know for finding this kind of a solution. So what you will do for finding the complementary functions, what we do for finding the complementary functions, what we do? I am taking di by dt plus I r by L is equals to Vs by L. So we already say for finding the complementary function we does not require our input source, so we'll make it as a 0. Okay, we'll discuss these things in a very deep in a maths. Okay, what is Bernoulli's theorems and all. Okay, so just okay, so I will make this as a 0. So di by dt I will get minus I into r by L. Okay, now find the value of I of t. I of t I will get, while putting this I will get, and this bringing this side, so let me bring I this side, so di by I and r by L into dt. Okay, so take from 0 to I and take this is from 0 to t. So you are getting here as a ln of I, and here you are getting this minus is there, minus RT by L plus some constant you will get, A, particular constant after solving this. So what I value you are getting, e power minus RT by L. I am taking that constant in terms like this. Okay, so this is my complementary functions. And for finding the particular integral, what you need to do, so particular integral will solve particular integral at steady state. So at steady state, how the circuit will become, this is my positive negative, this is my Vs, this is my circuit R, L will be short circuited. So what is the value of I you are getting, Vs by R, that's it. So I of infinity you are getting Vs by R. So what the function you got, this is my particular integral and this is my complementary function. Okay, so I of t you are getting how much, A e power minus RT by L plus Vs by R. Okay, now if you will substitute t is equals to 0, so I of 0, how much you will get, that is A plus Vs by R. So this at t is equals to 0 you are getting this, the value of A is coming how much, I of 0 minus Vs by R. Substitute this value in this equation. If you substitute this equation, I of t is I of 0 minus Vs by R, and this is minus e power minus RT by L plus Vs by R. So guys, what you will get, Vs by R plus I of 0. So I of 0, initial 0, the I of 0 was how much, I of 0 was 0, put the value of I of 0, that is 0, minus Vs by R e power minus RT by L. So this formula you are getting, this formula you don't have to remember like this, you have to remember I of t is nothing but I infinite plus I of 0 plus minus I infinite e power minus t by tau. So this is these things can be written as e power minus t by tau. Okay, so we are getting the inductor current formula, overall inductor current formula. that is I infinite plus I of 0 plus minus I infinite e power minus t by tau. When I was studying these things, I remember this formula like this: IL of infinite. I am writing the I infinite in a continuous way. So I infinite minus I infinite minus I of 0 plus whole bracket e power minus t by tau. So I was remembering like this. The same thing, because I took the minus common. So I infinite, then I 0. So I remember like this, and all the things is multiplied with e power minus t by tau. So guys, so this is the formula for your RL network. This I infinite is your called as a final value. Final value. Final value. And this I0 is called as a initial value. Initial value. With the help of this formula only, your transient chapter, you can solve each and every question of the transient. You need to remember this formula only. IL of t is equals to I infinite minus I of 0 into e power minus t by tau. The same formula you will get for capacitor. Will derive. Vc of t will be Vc infinite minus Vc infinite minus Vc of 0 plus e power minus t by tau. Here tau will be RC, and here tau value is L by R. We'll solve this also. So see guys, what we did, we have a RL network, R and L network. So what it means, before the switching conditions, the thing was the switch was open. So IL of 0 plus IL of 0 minus IL of 0 all was 0. When we switch this condition, when we applied the switch these conditions, we are getting the circuit like this. Okay, now we wrote the differential equations of this circuit. Vs by L plus I into R by L plus di by dt. Okay, so this differential equation, yeah, I hope you remember one form, dy by dx is equals to so these things we will study. I will not discuss here. We will study the auxiliary equation, differential equation, everything. So just you form this equation in the form like this: Vs by L plus I R by L plus di by dt. Okay, you form the equation like this. Now you got the equations like this. Okay, and you know, if the function is in the form of a differential equations, that can be break into two forms: complementary functions and particular integral. Okay, for finding the complementary functions, now you have to put the value of a input source voltage as a 0. Okay, complementary functions, that is, we are solving for a transient response. So that's why I just put the value of Vs as a 0. Now I have a equation di by dt plus I R by L. So if it will go in this side, and if we'll do the solution of this, and if we'll find the value of I of t, I will get some L and I functions. I'm writing here as a dash. Okay, if you will write this particular, suppose if you'll solve these things, you are getting I of t, you are getting e power minus RT by L plus a dash. You can write like this: e power minus RT by L into e power a dash. I am considering this e power a dash as a because it is constant only, so I took like this. Okay, so I am getting this is your what? This is your complementary function. And according to the definitions, so I got the complementary functions. And for finding the particular integral, see the definition. So natural response, you did it. For natural response, your input input voltage will be 0. The response of a network without the source present, without the source present in it. So that's why we neglected the source for finding the complementary functions. Okay. And for the force response we will source present. We have to consider the source at steady state. See the things, steady state response, and at that steady state your inductor will be short circuited. At infinite amount of time, that inductor having a zero frequency, then the inductor will get short circuited. And here the source, we have to consider the source. So that's why we consider the source, in particular this, and the inductor is short circuited, and we got the I infinite current. Basically you have to find the I infinite current. So you are getting the I infinite current as a I of infinite, you are getting as a Vs by R. Now you got this is your particular integral, this is your complementary function. Add those functions, you will get the equation of a current. So you are getting I of t is equals to a e power minus RT by L plus Vs by R plus Vs by R. Now, but the thing is that you don't know the value of A. Okay, no problem. We'll substitute t is equals to 0. I of 0 is equals to A. I of 0 is equals to A plus Vs by R. And the value of A will get I of 0 minus Vs by R. But we know the value of I of 0. That is 0 from the beginning. We got the value of A, that is minus Vs by R. After getting the value of A, substitute these things in your equation, this equation. I of t is equals to, and if you are substituting, you are getting Vs by R plus 0 minus Vs by R minus RT by L. So what is the Vs by R? Vs by R was steady state current, I infinite. Vs by R was steady state current, I infinite, and 0, that is I of 0. And I of 0 was initial current, I of 0 plus, and e power minus RT by L. So it is multiplying in this part. So e power minus RT by L. So we are getting the important formula, very, very important formula for a transient chapter. IL of 0 is equals to this. If you understood now, then the thing is very, very clear. If you will solve the problem, if you understood this formula, you will score 4 out of 4 in network. Means if the questions are coming from the transient part, if you understood this formula. Okay. And the same formula you will get for a capacitor, RC network. We had seen for a RL network. Na? Tomorrow we will derive for RC network. Or you just try by yourself also to derive like this. You will get the same formula, but the thing is that you have to change I with V, that's it. And you know the thing of a duality, you have e power minus t RT by L. Okay. For duality, this will be E only, e power minus t will be only, and R will become 1 by R and L will become C. So that's why you are getting the time constant C, and I will become V. So with the help of a duality also we can directly get the formula, but we will derive tomorrow that Vc of t is equals to Vc infinite minus Vc of t e power minus t by tau, in the same way what we did for this equation. So guys, you have to remember the two concepts. One is natural response and one is forced response. So natural response, transient, there will be no source presence. We are not taking the source. If the source is present, so we have to make it as a 0, what we did in this equation. And for this we have to consider the steady state value. at infinite amount of time, what will be the value of a current? And you need to find the equation. Is this clear to everyone? Or you guys having facing any doubt? Prasanna, Priyanka,
Clear, sir.
clear?
Clear.
Raj, for you?
Clear, sir.
Okay. So guys, we'll meet tomorrow. So that was a very important topic. So we discussed today. Okay. Good night.
Good night, sir.